let's apply.
Let's take a look at one last distribution using
a couple of distributions.
This is going to be a Weibull distribution. Okay, we didn't talk again much about the Weibull distribution in class.
Let's assume here that
we did apply the method of maximum likelihood because it makes for an interesting example. So let's go ahead and go through
machine or something like that.
goodness of fit test
breaks, and then we
for the
prepare
Weibull
it,
distribution.
and we
so we have some
want
failure
to
time
observe
data. Again,
the
failure
amount of
time
that it takes
often
to repair that
follows
machine.
a Weibull
Let's say
distribution,
we
which
observe
is
the repair time,
an exponential
50
distribution is a special
times. We have
case
50
of
different
a Weibull
observations of
distribution.
repair time. And let's assume that
And
repair time
let's go through the
follows
motions.
a normal
Okay, so what do we
probability
need to do?
distribution.
We need to
we'll
find
test
the
this
min,
assumption
the
later.
max, the
But
range,
let's just assume for now that it
the
follows a
sample
normal
size,
probability distribution.
the number of bins,
And so what we
and
want to
then
do is
ultimately
find
the
what are
bin
the
width.
optimal values
Were we
of
to
mu and
create
sigma
a histogram
that give
for
us
these failure time
the
observations.
best normal distribution.
So what's the
for
minimum
these
value?
50 observations.
Let's apply.
Okay, that's
the
essentially
minimum
what we're
function
doing
here.
with the method of maximum likelihood. We want to optimize, we want to maximize the likelihood that these observations
So the minimum
came
failure
from a
time
normal distribution
observation was
with
1.3,
particular values of mu
and the maximum
and sigma. Okay, so to do that,
is
let's first evaluate
139.7.
the PDF
So the range would be
for each
the
one
max minus the
of
min.
our realizations, each one of our observations of repair time. Okay, so we need to implement.
So the range is 138.4 time units
the
here.
PDF. We didn't use this a great deal
here.
in class because we had the standard
Let's
normal
just count
function,
these.
the standard normal tables,
Hopefully
to
we get
convert
35.
a particular
And we
value
do.
of y over to the standard
And
normal
let's calculate
distribution
then the
and look
number
up
of bins.
values
Okay,
of
so the number of bins
probabilities,
is going to be the
but this
square
would be
root
the
function.
PDF that we would use
Square
in the
root of
method of
sample
maximum
size.
likelihood.
Okay, 5.916.
To operate
we would
Excel,
like to
the Excel
round up
solver,
on that.
we need initial guesses
Let's
as to
round
what
up
mu and sigma,
no
these
decimal
two
places.
parameters, might be.
So we
Okay.
get 6 bins.
For
so
us,
the bin
we
width
even
is gonna
evaluate
be
this
the range
function
divided by the
at
number of bins.
y equals 278.2.
And let's
we have
round
to have
this
at
up.
least some kind of initial guess
Let's
for these
not
things.
go all the way up.
So
I
mu
mean, it's
is
close
the
to
overall
23.
mean.
Let's not go all the way up to
observations.
24.
We can just
Let's
kind
just
of
round
come up with
up
a
to
guesstimate of what mu might be.
highest decimal.
Let's
first
just
decimal, tenth
throw out
place.
the number 300.
So 23.1. How about that?
Mu for these observations is going to
So
probably
that
be
should
somewhere in the
capture
vicinity of 300,
all
maybe
of
a
our
little more, maybe a
observations.
little less, but that's at least a good start.
Okay, let's go over to the observed.
And then the standard
the
deviation
actual
here,
stuff that we saw.
let's just assume it's
Okay,
50.
the actual
Okay,
minimum
by
value
looking
was
at these
1.3.
observations, we might be able to
And we're going to
assume
have
that, sigma would be a good
6
starting
different
point.
bins here.
Pardon me, 50 would be a good starting point for sigma. So now let's evaluate
So
these
the first bin,
observations.
the upper bound on the first bin is
so
going
we're
to be
gonna
the
implement
minimum
this function over
plus
here. So that's 1
bin
divided
width.
by.
And since we're going to drag this down, we need to hold that bin width constant. Okay,
Sigma
so the upper bound on
times the
bin
square
number 1
root
is
of
24.4,
2 times pi.
on number 2,
It is a built-in pi
47.5,
function in Excel.
and so
P
on up to
I
bin 6.
and then
Okay,
parens.
the upper bound on bin 6 is going to be 139.9,
We'll close
which
these
captures
things up.
our maximum value of 139.6.
So this
So that's good.
is, and let's. I
So
always
now
get
let's
happy with
find
these
the number of
parentheses.
observations that would fall in
So
bin 1.
this is the first part right here.
Okay, so we're going to count
Now we're
if.
going to multiply that
We're
by
going to count in this range
the exponential function.
if
That's going to be negative.
the
0.5,
observation
negative 1/2
is greater than or equal to
times we've
this
got
value, 24.4.
our first observation here,
Okay.
minus mu
So what do we see? We see 26 observations
divided
in the
by
first bin.
sigma.
26 observations in the first bin.
Okay, I'm sorry. And we need to square
Less than or equal to
the
24.
y minus mu.
It was a little scary for a
divided by
second.
sigma.
9 observations in the first bin. We want to make
Close
sure
out
this
the
is less than or equal to 24.4.
Okay, so this is our first. This is our guess, our initial guess as
we
to
want
what
to do that
the
same thing down
PDF
here.
would be
But of course,
evaluated
what
at
did we see? We
278.2.
see that
What that
this is
evaluation
everything
look
that's
like.
less
What
than
would this
47.5, which
evaluated
includes
at y
everything
equals
that's less than
278.2.
24.4. We don't want a
Assuming
cumulative
that mu is
histogram
300
here.
and sigma is 50.
We want to subtract off.
Okay, and what we want to do here is not
everything
retype that equation
in the
over and
previous
over and over again. We just want to drag this
This is a
down
brute force
for
way to
all
do
50
this.
observations. But whenever
But
we
for
drag that
pedagogical
down,
purposes, it makes a lot of sense.
our mu and
Okay,
sigma are
so
gonna
now we've
change.
got
Those cells
everything
are
in
gonna
this
drag
bin
down
minus
with it
everything that
unless
was
we
before
hold
it,
them constant.
and we can just drag
So
that
we
on
need
down.
to hold these values
Okay.
constant.
So we should get,
By putting
when
dollar
we sum
signs
this up, we should get
in front of
35.
the row and the
we do
column.
not.
Really, since we're just going to be dragging this
So what
down
are we
straight,
seeing
we
here?
could put dollar signs just in front of the two rows, row 1 and
okay.
row 2. However,
Great.
let's just hold the entire
I would like to
cell
say I
constant.
did
It's
this
not
on
gonna hurt us
purpose.
either way.
So I'll say that I
So we're
did
going
this
to
on
put
purpose.
$signs in front of the
Whenever we drug this
column G
down,
and
the
the
cell
row
down
2
here and
to
down
hold
here and so
this
on,
sigma
what
value
happens
constant.
to the
And we do
range that we're
for all
counting
of
in?
the
Okay, it keeps changing by
times
one
that
cell.
G1
And
and
that's what
G2
happens
show up.
whenever you
For
don't
B2,
hold a
we
cell
wanna
constant
let that
when
roam
you
free.
should be.
Okay, whenever we drag
Okay,
this
so we
down,
need
we
to go
want
back
that to be
in
able to
and
change
hold these
because that
constant.
would change with our observations. But we want to hold those mu and sigma constant. Okay, so whenever we drag
And
this down here,
Then
we've got
that
all of these values.
that changed everything
for,
that we did
we've
here.
got all the
So let's
PDF
go back in
evaluations that are
and
different
subtract
repair
this off.
time
Okay.
realizations. Okay. Note here, for
And so
example,
on.
B6.
So now we get
our
a
function
total of 35.
drag down.
Okay, so in bin
B2
2 we
down
have
to
10
B6 whenever
observations.
we,
Up in bin
uh,
6 we have 4
drug the cell
observations.
down.
Okay, and the sum across all
Okay.
of those is all 35
So now what we could
observations
do
that we
here
should be seeing.
is evaluate our likelihood.
So now let's go over
function
to our
as the product of all of
expected
these.
observations. What would we expect to see?
What
in
does the
each one
product
these
of all of
bins
these look like?
if
It's going to be a very, very small
the
number. Keep
distribution
in mind,
is a
we're
Weibull distribution?
multiplying together.
Okay. Let's go back and think about
7,000s
what our
by 6,000s by 6,000s and so on. These are all very
what our
small
parameters
numbers.
were.
Whenever you multiply 50
Beta
very
and
small
theta.
numbers together, you get something
Whenever
that's
we
really
solve
small.
for
1
this
times
using
10
the
to
method of
negative
maximum
20
likelihood,
122.
we found that beta was
Okay.
1.3.
That may not be very efficient to try to
and we
perform
found that theta
optimization on a
was
number like that.
58.55.
So what we can do here is go ahead and apply.
So those were the
natural
optimal
log for
parameters
each one of
that we
these,
found
and
using the
then
method
sum
of
them up.
maximum likelihood, assuming that
The
these
reason that we
35
applied the natural
observations
log
came
in the
from a
analytical
Weibull
solution that we
distribution.
talked about in the
Okay, so
in
now we're
the,
actually going to determine is that
whiteboard
Weibull
video
distribution and actually
is
a
because
good
whenever
candidate
we
for
perform
these
calculus
data in the first place.
on the natural log
Okay.
of the likelihood
So
function,
now let's find.
we are performing
let's do this like we did with the normal distribution.
taking a derivative.
Let's find first
of
the
each one of
probability
several
associated with
functions
bin 1.
added up. If you
Okay, so we're
multiply
gonna
those up,
implement this
it
equation.
gets difficult. If you can add them up, it gets
This
easy.
cumulative,
Well, that also works
cumulative
here,
distribution function
because
for the Weibull
we're
distribution.
going to be dealing with
Okay.
a likelihood
You
function. It's not
can,
going to be nearly as small
find this
as
analytically using
1
calculus.
times 10 to the negative
Okay,
122.
going back to the
Okay.
PDF, little
So
f
we're going
of
to take
t
the natural
that
log
we
of each
saw
one of those,
in the previous,
and then we're going to add
one of
those
the
up.
previous videos.
Okay, so our natural log likelihood function
Take the integral
is just the sum
and find this.
of all of these values.
Or I'm sure you can find this on the internet, and in fact, Wikipedia will definitely give you the cumulative
Okay.
distribution
So
function
this is our
for
natural
most
log
any,
likelihood function
when
we
probability distribution you
assume
want to read
that
more
mu
about.
is 300 and that sigma is 50.
So let's implement
when
this.
we assume a normal
This is
distribution
1
for
minus
these 50 observations.
exponent.
So now this is the value that we want
minus
to maximize. We want to maximize
t.
the natural log likelihood
So here's our value
by
of t
changing these cells.
divided by
Okay,
theta.
we want to find where are the best values of mu and
raised
sigma that
beta.
maximize this function. To do that, we need the solver. So we go to the data tab and we go over to the solver.
And we want to make sure
function. Okay.
that
To add this in, I've already added it in on this
this
computer.
is all
But to add this in, you
inside
go
the
over
negative.
to,
It's a pretty
obviously I'm
important
using a
consideration.
Windows machine here. We go over to
We're gonna
options,
close off the exponent.
go into add-ins.
So what's the
and
probability
under the Excel
associated
add-ins,
with
if we
bin
were to
1?
Go to that is the
That's
solver add-in.
0.2561. Okay. That's the probability that an observation
So now let's
of a
use
Weibull
the
distribution
solver.
with these two parameters is
Okay.
less
You
than
can read up more about the solver. I'm
24.4.
just going to use this in a very rudimentary
Okay.
way. There's plenty
And
of
we're gonna
options
drag
that
this
we can
down.
look at here.
So we're going to
and
need
then
to
there's a lot of
hold
stuff going on
beta
behind the
and theta
scenes that you should be
constant.
a lot more familiar with. We're just going to touch on this very basic idea, and
But
that
not
is to
H.
set an
We
objective,
want this one to change.
which is this function right here, that cell. We want to maximize that by
Okay.
changing these two cells.
And so let's go ahead
Okay,
and,
we want
and
to
do all of
maximize
these
the natural log
probabilities.
likelihood function, which is found here,
We don't
by
want
changing the
cumulative
values of
probabilities,
mu
of
and
course.
sigma, which are
So
found
what we
here.
want to do is subtract
Okay.
off.
And we're going to do that with
for
an
each one of these.
evolutionary algorithm. Okay, this is just a heuristic algorithm. This does not provide us an analytical solution.
what was in the
We're not going to
previous
find
cell.
the exact optimal values of mu and sigma, but we're going to approximate them. So essentially, what heuristic algorithms do is,
Okay.
again, without
And
using
then in this
calculus,
last cell, if we just keep
they
dragging this down,
search for
if
a
we were to sum up these
ton of different
probabilities, we're going to get
values
something
of these
close to, but a
mu and
little
sigma
less than
here.
1.
Okay, and
Actually,
they
that's quite a
record
bit
the
off.
maximum. They record
So
the,
what we
the
want
mu and
here
sigma that
is
give the
instead
maximum
of
value
finding the
of
cumulative
natural log
probability
likelihood function,
evaluated
and
at
then they just
139
keep
and
searching
subtracting
over
off
and
this
over again until
probability.
they can beat
We want
that,
everything
the
that's greater
maximum that they
than
found so far.
116.8.
Okay, that's a
Okay?
quick
we
and
wanna
dirty
go ahead and extend out
explanation
to
of what
the
heuristic
upper tail,
methods
through the
do.
upper tail.
Okay, and one
all the way
such
out to
heuristic
infinity.
method is called an
Okay.
evolutionary
So to do
algorithm.
that,
Okay, and that's the one we're going to
we
implement
just
here.
want to say
To implement
1
this
minus
algorithm, we have to
the
have
previous
upper bounds and lower bounds for these
that
two
previous
cells.
cumulative.
Okay, so essentially we have to impose
Okay.
a
So what this
reduction
is
in the
saying
search
is
space. In other words,
roughly
we don't want
7.3%
the
of
computer to
observations
just
lie
search
above
every single possible value from
116.8.
negative 3
Okay.
million to
Note that's a little bit bigger than this one,
850
and
billion.
it's a little bit
Okay,
bigger
we don't want to
because
search
it's
that
including
much,
all of
okay?
those
Let's try to
probabilities.
narrow down the amount of
probabilities
work
of
that
all
the
realizations
Excel solver
to
has to
positive infinity.
do,
We're not just
with
stopping at
this
139.9.
evolutionary algorithm.
We're going all
Okay.
the way out
So let's
to
realistically add some.
So those are
bounds.
really small
So let's add a
likelihoods
lower
out there.
bound.
But
for
whenever you
mu.
sum them all up,
Okay.
you get something that
Let's
may
say
be
that
just
the
a
lower
little bit
bound is
bigger
not going to
than
get
that
any
previous
smaller
one.
than, let's say, 200. I
Now,
mean,
what would the expected
mean of
value
these
be?
observations
Well, we
is
just
not
have to
gonna be any
multiply this
smaller than
probability
200,
by
for sure. In fact, it's
the
probably
number
not
of
gonna be any smaller than
observations
250, but let's just leave it
in.
at 200.
Okay, we're going to hold that in constant.
And let's add
Because we
an
wanna
upper
drag this
bound.
down.
Okay, so mu must be less than or
Okay,
equal
so what is
to.
it saying here? This is
let's
saying
say
in
an
bin
upper
1,
bound here is going to be
we
500.
actually saw 9
Okay, the mean
observations
observation. Mean
that
of these
are
observations
less
is
than
not
or
gonna
equal
be
to
bigger than 400.
24.4. If it's
Okay,
actually
now
a
let's
Weibull
set,
distribution,
a
whose
lower bound.
parameters are beta and theta here,
Sigma
these
must be
optimal
greater
parameters
than,
using the method of maximum likelihood,
let's just throw a number
we would
out
expect
there,
to see
20.
8.96. And for this next one,
the
we saw 10,
standard
we would expect to
deviation
see
for these observations
9.46.
is probably going to be
and so on.
smaller than,
Okay.
let's say, 100.
We should, if we sum this up, we
Oops.
should get 35 over here. And we do.
Okay. So now
So
we've
now
got
let's
upper and lower
compare
bounds for each one of
the
our
actual
decision
and the
variables,
expected
the values
using
that we're
our,
solving for. We're going to use the
Pearson
evolutionary
chi-square
algorithm.
goodness
There are
of
some
fit
other
test.
options in here which you might want to take a look at, okay, just depending on what you need.
So how
Let's
different
start running the
is
solver.
9
Okay.
from 8.96
So the solver is
squared divided
um,
by 8.96
running several
And so on.
observations.
across all k
And
equals
it-
6 bins.
You know, we can sit around here and wait until
Our
the
test
solver
statistic
is
W is
completely
the
finished.
sum
Okay, that is that it's reached
all
some level
those
of error that it's okay with.
ratios.
That it hasn't improved the
Okay, we have a pretty
optimal
small test
value that it's
statistic.
found so far.
What
very
is
much. Or we could
the
set
p-value
with
gonna
the
be for this
options
test?
in the Excel solver. We could set an artificial number of
We're going to use
a
again
search
the
length or
chi
something like that.
square.
Or we can
this.
just use escape after a while,
right tail.
and say
That's
yeah,
going to be an
that's good
upper tail
enough.
test.
And
As
let's
always,
say that it's good enough.
this
We continue.
chi-square
or we could
goodness
just
of fit
stop. Let's
test.
just
Here's some chi-square goodness of fit test.
Save our
Always an
solution.
upper tail test.
And
We're always going to reject
what this says is
in the
based
upper
on,
tail, that would tell us that
however
this
long we
value
just
is
ran the
different from this
evolutionary
value
algorithm,
across k.
the optimal value,
Because we're
the
squaring this term,
approximately
it's always gonna
optimal
get
value
bigger.
of
It's
mu
never going to be in the
is
lower tail.
345.5,
Okay,
and
so
sigma
the value on
is
the axis is
43.2.
this W value.
Okay,
Our degrees
and
of
I ran
freedom
this previously,
would
and so
be
those were the numbers I
k
got
minus the
previously.
number of parameters minus 1.
So,
So
what
here
we're saying here
We have
is
k equals
the
6
maximum
minus
likelihood
the
estimates
number of parameters 2.
for a normal
minus
distribution
1.
to fit
So we have 6 minus
these
2,
50
which
repair
is
time
4 minus 1,
observations,
3 degrees of freedom.
are 345.5
So our
for
p-value
mu,
here,
43.2
0.51923.
for sigma.
big p-value.
That-
Bigger than
those are
any
the two
alpha we would
values
ever
of the
choose,
two
0.05,
parameters of this
0.1.
distribution
Okay.
that maximize
There is no reason
the natural log
for
likelihood
us to
function.
reject the null hypothesis.
Okay,
And so
we
what
didn't have to use calculus.
hypotheses are we testing?
used in this case
The null hypothesis
a
is that the
heuristic
data follow
algorithm
a
that's
Weibull
built into
distribution.
Excel. There are better algorithms. Okay, we didn't need anything really
And
hardcore
we are going to stick
solve
with
this.
That hypothesis.
There are better algorithms to use.
Unless
there are
the
other
evidence
more
tells us
sophisticated
otherwise.
software packages
The data
to use. But
do not
Excel is pretty
follow
ubiquitous.
a Weibull distribution.
A lot of people know how to use it, and this is a pretty straightforward kind of implementation.
Okay.
So if you have some observations, you could fit a probability
So
distribution.
we do not
Is
reject
this
the null
best
hypothesis.
probability
We
distribution to
conclude
fit?
that
Do
the
we
data
know that
follow
these
a Weibull
observations are normally distributed?
Okay.
We
Is that
don't
the
know
very
yet.
best distribution?
Okay, we'll run a
Perhaps
goodness of
not.
fit test to see
We don't really know for
But
sure,
if
but we do
the,
know that it's at least a candidate.
If the best distribution
Okay.
for these 50
at least a
observations is
candidate.
a normal distribution, then these are the
we
two
have
best
no
parameters to be
reason to
used.
believe, we have no evidence that suggests that the data do not follow a Weibull distribution, but we can't say for sure that the Weibull is a best fit. Okay? We just at least know that it's reasonable for us to assume that these failure time data follow a Weibull distribution with these two parameters. Okay? There are ways to compare the results of different tests to determine which is a good fit and which is not, or which is the best fit, I should say. But let's not mess with that. Let's just say that let's not reject the null hypothesis and conclude that the data follow a Weibull distribution. Okay? And much like with the exponential distribution, a Bartlett's test was a little more sophisticated, a lot more sophisticated than the Pearson test. With the normal distribution, we saw there were a range of tests that were more sophisticated than the Pearson chi-square test, including the Kolmogorov-Smirnov, among others. For a Weibull distribution, the more sophisticated test is called a Mann's test. Okay? And that's a pretty complicated test statistic, certainly more complicated than this one, and it's been empirically shown to be a more powerful, a stronger test, especially when you have a Weibull distribution. Okay, don't use a Mann's test for anything other than a Weibull distribution, but it's especially good for a Weibull distribution, and better, technically, than the Pearson goodness of fit test. Of course, this Pearson goodness of fit test, why do we talk about this one? Well, it's because it's ubiquitous across any kind of distribution. Okay, it's a very general kind of test. We're just comparing the observed value from the expected value. How different are those two things? How different is the actual data that we have from the data that we would expect to see if our data follow a particular distribution? We're squaring that difference, so we've got an upper tail test, and we're normalizing, in a sense, we're scaling by the value of the expected value. Okay? And then we're summing those differences up across the number of bins that we're using. This could be applied to any kind of distribution, discrete or continuous. Okay? It may not be the very best one for each individual distribution, but it's good for all distributions. And that's why we discuss it. Okay? For pedagogical purposes, and of course, if you need something stronger, you now know enough about what a goodness of fit test is that you can go look up what the test statistic would be for a stronger test if you need it. Okay, so that's the Weibull distribution. Answering a set of hypotheses about a distribution given the parameters that we found using the method of maximum likelihood.